another episode of The Savvy Entrepreneur. Today we have a real treat for you. We have David Giltner, who is a commercialization specialist who commercializes laser technology as well as helps other scientists get into business. David, how are you doing today?
I'm doing well. Tallis, how are you?
I'm doing great. I'm really excited about this conversation.
Me too. It's good to talk to you.
Yeah, absolutely. After my conversation with Christina, I was really fascinated about lasers. So when she made the introduction to you, I thought this would be a great opportunity for myself and the audience to learn even more about physics, science, and lasers. How about you give us a little bit of background on what you do?
Sure. So I'm a physicist by training. I started my career in physics. I studied laser spectroscopy, which is really using lasers as a measurement tool. I mean, it's a broad area, but think of using lasers to interact with matter and measure a variety of different things. For example, I did a precision test of special relativity using atoms as clocks and measuring the difference in a particular atomic transition when an atom's going fast versus slow, right? This is Einstein's theory, and it's been validated or verified at a number of different levels over the years, but we keep improving the precision on that because as soon as you find a gap between the theory and the experiment, there's new science in there, right? So that's an example of the types of things that I did. But when I got my PhD, I decided I wanted to go into industry. I didn't want to be a professor, maybe what's considered the classic uh, scientist career. And so I spent a career commercializing laser technology in a variety of different applications. I started out in scientific instruments. Most of the time I was working in telecommunications and datacom, so using lasers as a communication tool, and a
Like
little bit
fiber
even in
optics?
satellite. Yeah, most of it was fiber optics. That's right, exactly. Both in long distance, hundreds of kilometers, as well as short distances for data communications within a building, kind of a thing. And also some time at Ball Aerospace doing satellite communications, so no fiber at all. Yeah.
So like line of sight laser communication?
Yeah, exactly. So, in principle, it's all the same. It's. I think of it going back to some of the earliest optical communication was probably, we've heard of like using a mirror from one ship to another and communicating in Morse code. Well, the way it's done now, really, in principle, isn't any different. It's just that we can blink the light on and off way faster, and in gigahertz or billions of times a second, and we can go much further distances because of optical fiber, long glass fiber that carries the light. So yeah,
So that's kind of like the new light Wi-Fi technology, right?
that would be an element of it. Yeah, sure. I mean, there are many ways you can communicate, and Wi-Fi, long distance. I mean, it's a pretty versatile method of communication now.
Let's go back to Einstein. So when you're saying this involving Einstein, I'm assuming you mean theory of relativity.
Yes, and specifically the special theory. He's known for
Is there a non-special theory?
there's a special and there's a general theory of relativity.
Ah,
Yes.
okay.
So the special theory of relativity came first, and and so I know you've got a very broad audience, right? Probably from other scientists to so to put it in simple, easily understandable terms, that's the part of his theory that suggests that for an observer moving very fast, and by very fast we mean close to the speed of light, 80% or so, time is the speed of time is different than for an observer not moving. Now, relativity actually also says that at constant velocity, there's really no, you can't say one person is still and another's moving. It's the relative motion that matters, and so it gets pretty interesting if you dig into that. But in our case, we were using atoms and the atomic transitions that happen when an atom absorbs light of a particular frequency. Well, that frequency effectively serves as a clock. And so, a simple way to think of that test is if an atom is sitting at rest relative to our laser, it will absorb light at a particular frequency.
Hmm.
If it's moving, it will absorb light at a different frequency. And if it's moving really, really fast, we should be able to calculate that shift in frequency by Einstein's theory. And
Hmm.
so essentially what we did is we took one atom that was basically at rest at a lab here in Colorado. and another of the same atom, it was a neon atom, that was moving very fast in an accelerator in Denmark, measured the exact same transition and compared the frequencies and compared that to the theory. In a nutshell, that's how that experiment was done.
Wow. That sounds really similar to like quantum mechanics.
Well, it certainly leverages a lot of quantum mechanics. I mean, the details of an atomic transition, how an atom might interact with an electromagnetic field, or in other words, how an atom might absorb a photon. There are few ways of describing it. The details of that are absolutely quantum mechanics.
So it might sound like I know what quantum mechanics are, but I absolutely don't. Can you give me a quick, or maybe not quick, but a understanding at a high level?
Yeah, sure. I mean, it's one might say. In fact, I think it was a pretty well-known physicist, Richard Feynman, I believe, made this comment that if you think you understand quantum mechanics, you really don't understand quantum mechanics. And the point of it is, it's difficult to get an intuitive understanding of, right? We have math that it works. It's used in a lot of different things, but an intuitive understanding is hard. In short, what quantum mechanics tries to do or does describe is very, very small things. So, classical mechanics or Newtonian mechanics described how large things work, a ball rolling down an incline, or something bounces, or even planets moving according to gravity, right? That's the stuff you might study in a college physics course. But when you get down to things that are on the size of electrons and protons and the wavelength of light, things like that, things start to behave a little differently. And so we've had to figure out new ways of explaining that. And some of it is counterintuitive. Something people may have heard of, for example, is an electron can behave both as a particle and as a wave,
Huh.
depending on how you interact with it. Or light can behave as a wave. We all know light behaves like a wave. We talk about it, we describe it as having a wavelength, but we also call it a photon sometimes, which is a particle. That
Ah.
maybe is the most common example of that. And it all depends on how we're using it. Einstein actually discovered what's called the photoelectric effect. In fact, that's what he got his Nobel Prize for, not
Hmm.
relativity like many people think. The idea that if a photon interacts with the right material, it will eject an electron, and that can cause. You can use that to generate current, right? And in the end, a solar cell functions that way. That's where it's behaving like a particle. And it turns out, you can quantify and quantize the energy involved, and there's the energy of the photon and the energy that the electron is ejected with. But in different scenarios, you can interfere light waves. You can see interference patterns, which suggests it's behaving like a wave. Uh, that's in a nutshell maybe the most common of elements of that. But there are many other aspects to it as well.
And then in space, things act even differently, right? I mean, you have high energy particles bombarding space stations that can cause like massive, damage. I know from one of the companies I work with, when we spoke to astronauts, when they would close their eyes, they would see flashes of light, and that was apparently high energy particles hitting their eyeballs.
Okay, interesting. I'm certainly aware of what you're talking about. I have not heard that you actually see flashes of light. Yeah. So, there's all kinds of things out in space that are typically higher energy particles and radiation that are typically screened out by our atmosphere, that are an issue out there. Yeah, that's true. That's very interesting.
So that was your previous life. What are you doing now?
Well, now I have my own company. I started this in 2017. I had a job developing, commercializing laser technology, as I mentioned, for a variety of applications. But in 2017, I left that job and I started my own business. And what I do is I help scientists commercialize technology and also design, and build their own careers in the private sector. So it's really about taking all of that I've learned, both about how I, as a scientist, made the transition into the private sector, because it's a very different environment. But also then how we take things off a science bench and turn them into products. I think you've got enough experience with commercialization yourself. You're aware of that. That's what I've done my whole career. The new part that I'm focusing on more with Turning Science is actually on the scientists themselves. That receives a lot less attention. There's, as you know, there are many efforts, incubators. The university here in town does a great job of looking at helping people commercialize technology, right? There's a lot of focus on that. There's less focus on the scientists themselves and helping them figure out how to transition from an environment where they've been a research lab until they're almost 30 and learn habits and then step out into the private sector where it's a different environment and make those changes. I know I struggled with that in many ways myself. So I help others do that.
That's really great. And I think that's a really needed thing because I know a lot of very bright scientists that have some really world changing inventions that they're unable to take to market because that's just not in their skill set.
Yeah, I mean, that's absolutely true. You describe lots of scientists. Some don't even have an interest to do it because they want to stay in university. Others do have an interest, but yeah, that's not what they've been trained to do, you know. I mean, there's certainly overlap, but academic research and industry are different in some very key ways. And as scientists, we are trained in academic research. That's really how our advisors typically groom us. Some professors certainly are very active in the private sector in collaborations or spinning out startups. No question about that. But by and large, particularly in science departments, there's just not a lot of even understanding, much less focus on what is done in the private sector. And so we tend to learn habits in academic research that actually are often counterproductive in the private sector. So, you know,
Totally.
you say it's not in our skill set. Sometimes it's almost the opposite of what we have learned to do in some cases.
Yeah. Another thing is that academics is very siloed. So sometimes a project may be interdisciplinary. And if you don't have the perspective of, if you're a physicist and you need the perspective of a chemical engineer or a mechanical engineer or something, that isn't really achieved in academics because everyone is in their departments, right?
Yep. Yeah, I mean that's, you know, I was a physicist, right? That's all I did. I'm encouraged by so when in non-COVID times I travel a lot because I visit universities and companies and things. There actually are a greater degree of science departments that are doing a lot of interdisciplinary work, and I'm very encouraged to see that. But historically and in many universities, you're absolutely right. And I mean, that's one of the first big deltas, the first big gaps. You get out into the private sector, and you'll almost certainly be working with people with very different backgrounds, either technical backgrounds because they're from a science discipline or an engineering background, or, of course, people who aren't even in science because that's what you need to make a company run. And that can be one of the big changes, one of the big gaps. You know, we learn the habit, and frankly, we're groomed to be the expert when we're getting a PhD. Even though some labs have more collaboration these days than they have in the past, you're solely responsible for your project, and that tends to groom you to think, okay, I need to solve this myself. Right? I need whatever it is. I need to learn this myself, and when it's siloed, well, that makes that easier. That habit carried into the private sector can be very difficult. So yeah, I it's funny. I was watching a pitch. So we're both involved in startup activities, right? I was watching a pitch of a local company called Living Inc. And Scott Fulbright is the founder. I don't know if you heard of him. He's a PhD biologist, and he was talking about his company. And at some point, he stopped and he said, "You know, I have found that in some ways, graduate school prepared me for the opposite of the real world because it taught me to work alone." And one thing I've learned in the private sector, and absolutely starting a company, I cannot follow that habit. I have to count on other people. And the tendency to work alone, to think I need to figure this out myself, just slows you down. I've had to get past that. And I thought, I wrote that down. I use that quote in a lot of what I do because it is so true, right? In some ways, graduate school prepares you for the opposite of what you have to do out in the private sector in the real world.
Yes, especially in entrepreneurship. I mean, maybe corporate environment's a little bit closer to academia, but like in entrepreneurship for sure. For example, um, I was working on a project, and the scientists, they wanted it to be perfect, absolutely, like
Hmm.
without any, nothing wrong, absolutely perfect, right? But that's impossible to do in an entrepreneurial environment because you have limited time and resources. You got to go to market, you got to like get feedback and iterate, and none of that is really was you they weren't used to any of that. So it was really teaching a brand new way to look at development.
Oh yeah. So you pinpointed another big gap, and it shows up in a couple of different ways. I think that working for perfection is absolutely right. It tends to have us working on things that don't really we don't focus on the result that's needed, right? In the private sector, something has a specification usually, and that's meant to say this is good enough. Work to get to that point and stop and go work on something else because the customer's not paying for more than that. And the idea of a scientist who wants to keep working and I can get 20% more output or I can make it a little better, like, why would I pay you to do that? Because the customer's not paying me for more. Is that perfection? The other place it really shows up is in the hesitancy to make decisions because we want the right answer. We are used to, science can be very slow because the emphasis on certainty. And we can take the time we need to be certain. And as you pointed out, certainly in an entrepreneurial situation, and frankly, in any private sector situation, speed is always important. You always have competitors. And also, many of the decisions aren't purely technical. So I like to say there's really no right answer to most of them. In a science lab, yes, we're chasing a right answer. We're looking for the formula that will demonstrate it. In the private sector, you need to make a decision and move forward. And you don't always have all the data you need. A lot of times you don't. You don't know the answer. So that's an important gap that I see a lot.
Absolutely. I think that understanding that there's not just one right answer in business is critical. When I was teaching at the University of Colorado, all my students were like, can you give me a template for a business plan? Or can you give me a template of what I have to, and I could fill it out? It's like,
Yes.
it's not really how business works. There's infinite numbers to get to the same positive result. So you just
That's
got to figure
exactly
out what works for you and your team, right? And your
That's
product.
exactly right. A phrase that I started using, it's actually one of the principles of turning science, is I say it's a game, not a formula. And that captures so many of the struggles that I see scientists doing. And it's just like you described, right? We're looking for the right answer. What's the formula, the checklist, the something? And private sector does not work that way. It's much more like a game where there's many ways to win. And what you need to do is take what you've got, play the game, and try and find a way that works for you. Quit looking for the one right answer because that leads to an attempt for perfection and going slowly. Take a
And
shot.
a paralysis through analysis.
Absolutely. Yeah. Yep. So, yeah, that really captures it well.
David, you've been doing this a while. Is there any products that you've successfully commercialized?
Yeah, so there are a number of them. Let's see. One of my favorite stories is actually fairly early in my career. So, my first job right after my PhD, I moved out to California and I joined a company called SDL Incorporated. It stood for Spectrodiode Labs. They made diode lasers. They ended up getting folded into JDS Uniphase, which is pretty well known in the telecommunications area. But I started out working on instruments, science instruments for labs, and the concept was to try and get new technology, fiber laser, fiber amplifier technologies, out into universities to try and scare up some commercial applications. And telecommunications is one of the big ones that came out of that. One of the first real products that I developed, and it was a great learning opportunity, was a high power fiber laser, a watt output. And this was the first commercially developed and what was called Telcordia qualified. It's a set of qualification criteria for telecommunications products, right? In terms of physical robustness and life test and stuff. We actually put together this high power cladding pumped fiber laser product and qualified it and sold it. And that was, it's both a success story, but it is also that's how I learned so much about how you turn something into a product and what's required and how you lead a team to do that. It was in that project that I had a great boss and mentor, but I also had a team, and it was during that time that I moved into managing a development team. And how do you work with? We talked about different disciplines, right? And how do you get them all coordinated on doing something with a timeline, a schedule, figuring out how good does it have to be, and don't make it perfect. Uh, and what the customer needs, starting to interact with customers. I mean, the learning curve there was really something, and that's still one of my favorite experiences, I think. Um, from there, I did more work at Tula Communications in that company. JDS Uniphase is what they became part of, and that was all along similar lines. Um, at some point in 2003, I decided to move back to Colorado where I had lived before. And that's when I worked for Ball Aerospace. That was pretty cool. But I think the next most interesting, in terms of how interesting it was, is probably the last job that I had. So from 2010 to about 2017, when I left and started turning science, I worked for a company called Zolo Technologies that is now part of Koch Industries. It was purchased by them, um, putting laser-based combustion sensors on industrial furnaces. So this was a laser spectroscopy, a different kind of spectroscopy type of product. Think of so one thing you could measure with laser spectroscopy would be an atomic concentration. You can measure how much of a particular atom is in the laser path. So if you shine a laser through a big furnace, imagine a huge furnace, 100 feet square. You're throwing in some kind of fuel and oxygen, and you want to know how well is it burning because it's so big and it's hard to get that burning well. Shine a laser through it. If at the right color, you can measure how much oxygen is in the furnace. You can measure how much carbon monoxide is being created. You could measure how much carbon dioxide is being created. You can measure the temperature. And so we were developing a system based on that. And the system was basically together when I was there. I mean, they had already were building and shipping this, but we moved into some new markets and definitely made it more robust. You take something that's like this is really you can imagine it as a science project, and now you're going to put it not just out into the field, but at a factory, a refinery or a steel plant or a coal-fired power plant where it has to be very robust and operate, and it has to be operated by people who have no idea how it works, right? I mean, the operators, they understand fans and pumps and burners. They don't know anything about a laser. So that was another huge learning curve in terms of how do you commercialize it, how do you help people use it, how do you market it to new customers. That's when I moved into product development, product management, and business development. So that was another big learning curve and just a really interesting path.
Yeah, I mean, it's fascinating. Think about the tough conditions that you'd have to design that product for. I mean, the temperatures, the gases, and everything. I mean, that must have been quite a feat.
You yeah, you have to be okay with things not working, right? Because that's how you learn it. It at first it almost sounds crazy. Oh, you're going to shine a laser through a big dusty sooty furnace. How are you going to do that? And you have things that don't work well, and you have to get in and figure out how to make them work well. Yeah, definitely an interesting.
And reliability is key because I'm sure that would cost millions of dollars to have to go in there and fix, right?
Yeah, I mean it's a lot, maybe not $1 million because nobody millions, but definitely in that scale. Yeah, I mean it's you're talking about a product that's in the $500,000 kind of ballpark range, right? And so they've paid a lot for it. They want it to work. It's this was not just a box, right? This was a whole system that was actually assembled as it was being installed. This isn't like a box you build and test at the factory and then you ship it to your customer and it works. This has to be assembled in place.
A lot of customization, I'm sure.
Yeah, and a lot of customization. That's right. The goal for any product is to make it scalable, and that is you try to make everyone as identical as possible. That has limitations sometimes, and yeah.
What do you think the hardest parts of getting over the scientific mindset and getting into a business mindset are?
Yeah, that's a great question because while there are many strengths, let me talk actually first about the strengths because that sets up some of the challenges for the scientist becoming an entrepreneur. A lot of people look at those two different career paths and they say, "Wow, these are very different, right? Can a scientist really be an entrepreneur?" And they can. There's a few things that are really good about that. One is we're great problem solvers, right? One of the scientist entrepreneurs I interviewed said one of the great things about a science education is you're learning to solve problems no one's seen before, and that is a big part of being an entrepreneur. We are independent learners. That's what a PhD is all about. Is you're presented with something nobody's done before, and you basically on your own have to figure out how to do it. Well, that starts to sound like entrepreneurship too, even though a lot of science PhD students don't really realize it. The other interesting one, and a scientist named Peter Fisk, who is he's at Berkeley in California, but he was a startup founder for a while as well. He said, "Well, scientists are resourceful, and that's really important too. In the lab, they get good at doing great things without a lot of money, and that certainly sounds like entrepreneurship. But they even have to do it in their private lives when they're graduate students, right? You have to live on a $1,500 a month stipend or something. And so it's not just in your work, it's in your private life. You learn to be efficient." And he said, contrast that with a lot of people think a business major might be the perfect entrepreneur, but, take somebody that they get their MBA and they go work at Morgan Stanley and they've got their BMW and a penthouse, and then they decide they want to start a startup. Hmm. So
Opportunity cost is way too high.
yeah, that's right. So those are some of the challenges, or those are some of the strengths, but some of those can actually be challenges, right? The independent learner means, as I described before, we tend to want to do everything, and you just can't do that in the private sector in general, and absolutely not as an entrepreneur. You have to find people who can help you out, right? That's just one of the big challenges. And so that's maybe one of the big things. Being slow to decide, that is also an important thing. I mean, I like to say that being able to make decisions when there's no right answer, that's actually a critical part of leadership. There is a job where it's your job to figure out the right answer and implement it, and that's where scientists sort of signed up. That's the career we signed up for, finding the right answer. But when you get into the private sector and absolutely starting a company, there will be questions that have no right answer, and somebody has to make the decision. Well, when you're an entrepreneur, that's you. You were the person doing that. And all of a sudden, the habits of a scientist of trying to find the right answer, of getting to perfection, of needing more analysis and more data really counteract that challenge, that make that a challenging thing. And so those are maybe the two biggest challenges that I think they face. And so working with them to help them learn to make decisions. Uh, so one of the things I teach actually is a technique. Making decisions is never easy, right? So it helps to realize, look, at some point you're not going to have the right answer. You need to make a choice. I like to say the technique that I use myself and that I teach is when you've eliminated the dumb decisions, you want to do that. Analysis is important. Don't just make a crazy decision. And you're down to two, maybe three things where you're not sure which way to go. I say pick one, make a choice, and then work to make your choice the right decision.
Yeah.
And does it make sense? I mean,
Yeah, absolutely. Hmm.
I like it for two reasons, and this is why I say it's been useful. First of all, it reminds me my ability to predict the future is not nearly as good as I'd like to believe it is. Right? I mean,
Me too.
I know we all deal with this. My experience, I think scientists might be even worse because that's what we signed up for in a career. Everybody struggles to make hard decisions, but when we come out of an environment where the whole idea is to get the answer from data and analysis, it's natural to think if I just collect more data or I do more analysis, I'll get it. But what you're really trying to say is you're trying to predict the future. And history says, I'm not very good at that. And this reminds me of that. Trying to beyond a certain point, you're wasting time. But the other thing is, once you make a choice, make a decision, there's actually a lot you can do to make it work out. First of all, you can get your team involved and say, okay, here's the way we're going, help me make it successful. And it's certainly no guarantee that you're going to be successful, but you weren't going to find the right answer anyway. And once you start moving forward, now you're dealing with real problems. Well, I know how to address real problems. Before I make the decision, I'm looking at hypothetical problems, and I don't know what to do with hypothetical problems, right? I know how to address real problems. So once you start moving forward, you run into what actually happens instead of trying to predict what might go wrong, which might be right and it might be wrong. So that's why I like that technique so much. That's among the most powerful things I think for moving forward, and and then of course having the right people on team, as I'm sure you're well aware, is important because they can help you with the challenges. They can tell you when, hey, maybe you're not being, we're not making decision as quickly as we ought to, or maybe we're trying to be too perfect. If you have the right people on your team, they support you through all of that.
Mhm. I'll give you a great example. I completely agree with everything you said. One of my companies, BodyFit, we had a IoT device that can capture movement and give feedback on form, right? So there's two obvious markets for that. There's a fitness market and then there's a physical therapy market, right? They're both very large, but for different reasons, right? I mean, physical therapy, you charge a lot more and there's a lot less, but you know, consumer market massive, but you can't quite charge as much,
Mm-hmm.
right? So there's a whole lot of calculus in deciding which one. We ended up, waffling, going back and forth, wasted so much time. If we had just picked one and then executed and then see what market said and then made adjustments based on that. I mean, it was one of my earlier companies, so I learned a lot from that I don't do today, but
Mm-hmm.
it's definitely something that you should take into consideration. Make the decision, be definitive about it, but also be open to making the change when it's abundantly clear that you made maybe the not right decision.
Right, because there's no guarantee, it will work just because yeah, no, you're right. And your example of two different markets like that, that's a perfect example. And that because I've seen people do that. I've had that question myself. There are numbers involved, right? Price, volume, and those kinds of things can trick you into thinking maybe there's some analysis that will tell me the right answer, right? But from your experience, I mean, you don't really know how those are going to work out, and there's too many variables beyond the math. It's far better to pick one and say, okay, how are we going to make this work based on what we've chosen? You're absolutely right. That's a great example.
To steal a cliche, fail fast, right?
Yeah, yeah, that's true. I mean, that's where that comes from, right? It's not saying that we want to fail all the time. Of course not. What it's saying is be open to making a mistake and doing it wrong. That is part of that, look, you're not committing yourself. Just because you say make a decision and move forward doesn't mean that you are absolutely going to do it that way and no changes. No. What you're saying is we're better off moving forward and seeing what actually works so then we can address reality rather than continuing to try and analyze and predict and come up with a model that is never going to be perfect or complete. Figure out what works or not, and if it doesn't work, well, pivot. You can probably find a way to, as long as you're paying attention. Few of those decisions truly end up being fatal if you're open to being flexible and if you're watching as you move forward.
Absolutely correct. So another thing that I would like to talk about is understanding the core of your product.
Mhm.
Another example from BodyFit is we started off with the idea of capturing movement and analyzing movement, but then we fell into the feature creep trap where we
Mhm.
wanted to add all these other cool things. Like, what if we added a EKG so we could look for sudden cardiac arrest warning signs? Or what if we looked at your salt content of your sweat to see whether you're dehydrated, or see whether you should increase your potassium level? All these things were really nice to have, but after analysis, we realized the customer didn't want it. So I'm sure you've had plenty of examples of feature creep, right?
Oh yeah, yeah, that's a good one. In fact, we talked about scientists wanting to make things perfect and keep improving them. I find scientists might be among the worst at allowing that. I mean, I want to do it myself, right? I that temptation when you say, hey, and this product we could add this. I, I still struggle with that because you just always want to make it better. And the savvy entrepreneur, the savvy business person is able to back away from that technology infatuation or feature infatuation and say, hang on, we have to make a viable product here, right? We have to understand what the customer will pay for and what they won't. And it may be great to add something, but that doesn't mean that they will pay for it. And it doesn't mean it's a viable business, right? When I talk about developing products, I focus on viable as one of the important things products have, and I really try to get them to focus on what is the problem you are solving. Not the nice to haves, but what's the problem. And I even go further and say, okay, once you define that problem, what is your customer, your target customer, currently doing to solve that problem? Because if they can't identify that, it's probably a nice to have, right? If they're currently doing something to solve the problem, and then you can start to ask the question, how much will they pay for your solution versus the other? That's a path to what's really important, to the part of it that matters. If it's just, oh, they'll be excited by it, that's we ran into that in at Zolo, that what I was telling you about it, customers that would try a new one, and the engineering team would be excited. Oh, we've got eyes in the furnace. We've got data we've never had before. And, and some of them, we sell one without really taking it to the value proposition, which is how will they actually use it to save money? And we realized, okay, this is important. Having a team that says, hey, it's really cool, is not going to help them buy a second one, because the person writing the check is going to say, how did you make money with it? Not was it cool? Was it great? Did it do all these gee whiz things? But how do you make money with it? And that really focused us.
That's so true. And I think what you're really hitting on is the key difference between a feature and a benefit. What you want your customers to have is the benefits, right? But just because you have a feature doesn't mean it's going to add any benefit to the
Mhm.
customer, right?
Yeah, that's right. That's right. I really coach people to look at the value prop, and in dollars or in euros or in yen or whatever currency, right? In money. It can be, again, it's that technology infatuation that can say, oh, it makes this easier, it makes this better or cooler. But the benefit for a business, for somebody writing the check for your product, is going to be savings in some way. More profit, more savings, something that turns into money. And so it really makes sense it's really critical, frankly. I'll say more than makes sense to have predicted that, to figure that out in advance. Are the features you're adding only features, or are they benefits? Do they produce value in a monetary sense? And that is the key to a successful product, right? It's not about, innovative technology sounds great, but that doesn't support a product. Solving a problem, a real tangible quantifiable benefit to the customer, that's what a product is based on.
Wholeheartedly agree. Absolutely. I learned a lot in this conversation, and I'm sure our audience did too. Do you have an ask for our audience?
Yeah. So, if you're interested in this, I do a lot of helping anybody, but scientists and engineers in principle, or in particular, really figure out how to commercialize technology. Go to my website, turningscience.com. I give workshops and a lot of training and things, and specifically around product commercialization, technology commercialization, and product development. It'd be great to hear from somebody who is interested in how can they do this better, because that's what I do.
David, that's great, because I think that commercialization is key for a successful product launch. So if you have a product and it's a science-based venture, I highly recommend you reach out to David, and he can give you invaluable advice. So don't miss out. Take up this opportunity.
Sounds great. Thank you.
Until next time, stay savvy.